Hello, afternoon, guys. We are going to look at the second lecture on induction motors. Yeah, I hope you guys had time to go through the last the introduction. I saw there are about 21 views, so which means hoping that everyone who viewed managed to watch the videos anyway, which means that you guys are watching. So today I'm going to look at the equivalent circuit diagrams for the induction motor. The last time we just described its characteristics, we described its formation, construction basically, and a few small things that we calculate in the beginning, a few terms that we would need as we continue our studies on this. Okay, so I'm hoping that this will probably be also less than an hour, because I don't want to, have those large videos. Hence, I'm also stopping the MS Teams, because those ones tend to be pretty long. And now, for someone to watch a 2-hour video is something else. Okay, so introduction, still an introduction to induction motors, but we're looking at the equivalent circuit diagrams. All right, so I'll go through the lectures, then I'll be switching from the lecture to my board to the lecture also while we are explaining this stuff. Okay, so I'm using these lectures so that I don't skip stuff, because there is stuff that is important that we don't want to miss. Okay, all right, so already we explained that an induction motor, basically power is transmitted by induction, meaning that it can be given in form of a transformer, where we have the secondary winding of the transformer known now is known as the rotor, and it rotates. Okay, so that is the difference. So that means we can actually draw the induction motor as a transformer with just a few tweaks. Okay, so that's what we want to look at. Right, so let me see if there's anything that you need to know here. I don't think so. You will have to go through the notes yourself. I just want to look at what I will have to teach you, and then I explained it on the board. All right, so now we all know this circuit to be the transformer circuit, just like a transformer. As you can see here, you have if it was a transformer, then this would be the primary side. These are the primary quantities, and then these would be the secondary quantities. But now, since it's an induction motor, we now have RS now represents the stator resistance. When we say stator resistance, we're talking about the winding resistance. Now, what we are looking at, remember, this is a 3-phase induction motor. But when we are drawing this, we are not drawing it with the 3 phases. We are drawing it per phase, yes, per phase. So you will see that you have these terms here, per phase stator winding. So this is basically looking at one phase. Whatever happens through one phase is what you're looking at. And then so if you multiply by 3, eventually then you'll see the total power that is being transmitted in the induction motor as a whole. So now S represents stator and R represents rotor. So it's simple. It's the same way, this is stator resistance, this is stator reactance, and this is what? The core loss resistance. Now the core loss, because remember we still have laminations of those core materials. You saw in the video where we stacked some laminations, so there are still core losses. Remember, these are due to eddy currents, right? All right. And then we also have magnetizing reactance, because there needs to be magnetization. It's still some sort of a transformer. So some current needs to be pulled for it to operate even on no load. Right. So these terms we already know. This is loss. This is the no load loss. This is just the no load, and this is the no load magnetization current. And this is what? IR prime. Remember, it is the one that is reflected from the secondary side. So on the secondary side, we have IR and the reactance, and the rotor resistance R. Rotor resistance, we're talking about the winding resistance. Okay. So now, so far, if you look at this diagram, it's not giving us any information about the shaft, what is being turned. Remember, because an induction motor, we are trying to have rotation, and then so that we can use the rotation to do some work. But where do we get the rotation? It is the rotation that is on the shaft at the end, right? Output shaft. So in this case, we have not yet talked about the mechanical power that goes to the shaft. We are basically looking at the losses that are in the coils, in the rotor coils. So here we have a rotor reactance and then rotor resistance. Okay. All right. So this is looking fine so far. So this is rotor EMF, the EMF induced in the rotor coils, and this is the stator EMF, the EMF induced in the stator coil. So far, there's nothing new. What you just need to remember is XR is calculated is what? 2 pi FL, right? So in this case, since it will be inductance of the rotor, it's called LR, like this. Okay, I will explain this SCA. I will explain it in detail as we go. All right. So that's what the rest is just explaining the air gaps and stuff. You go through these notes, you go through them. Now I want to look at these, so I'm going to shift from these notes so that I won't be like I'm just explaining the slide. I want to, if we start writing from, I understand, it will be better for us if I do that. So let me just start it this way. I don't know what is happening. Oh, yes, right here. It's playing with me, eh? Okay. All right, so equivalent circuit of an inductor. Equivalent circuit of an inductor. So already we have our circuit. As we know, we have a resistor there, inductance, the reactance there, a resistor here, and reactance there. And then we have our coil right here. Okay. And we have the secondary part, coil right here. And then we have our reactance, and in this case, they're just putting the resistor right here, but it's still the same. Because now all you need to know is that the difference with this to the transformer is that the transformer normally is like that. The secondary circuit of the transformer is like that. And then this part here is open on the secondary. That's where we connect our load. But in this case, this guy, it's a closed loop, but it is connected somewhat to the shaft, not electrically. Yeah, the shaft is the one that is connected on the, I don't know how it's connected on this. On the rotor, you can check it, like, remember I showed you the video. So the shaft, that's where our load is connected. So it's not electrically, our load is not electrically connected to the secondary side. There is no electrical connection between our load. Remember, the load can be you trying to lift something. So that's nothing electrical, okay? All right, you will see that later. Okay, that is not electrical. Okay, so so if we are going to label this, I say this is the stator resistance, this is the stator reactance, and this is I no load. You can call it a no load. You can, the way you know it, no load. It's just no load. And then the current that is flowing here is I no load M, and this is J X M, and this is I. You can call this I no load loss, the way you know it, and this is RC. Okay, and then here we have I rotor prime, Here we have I rotor. Here we have J, X rotor. And here we have R rotor. And then here we have E rotor. Here we have E stator. So what I'm going to do today is we're going to be changing these things. So let's say this is the per phase supply. This is the supply per phase. This is, remember, this is a per phase equivalent circuit. Per phase. Okay, so we are going to break down this circuit and change it and change it and change it until it becomes what we want it to be. We're going to play around with the circuit. And then the turns ratio is called the effective turns ratio here. Still, the same way the effective turns ratio. It's just that it's easier to see in a wound rotor, where you'll be given it's just the number of conductors in the secondaries in the rotor over the number of conductors. Sorry, the number of conductors in the stator over the number of conductors in the rotor. But then when it's in a squirrel cage, it's pretty difficult for you to count the conductors because of the arrangement. But I'm sure they'll give us enough information, and then you'll be able to find it out. But it's still ES over ER. That's our turns ratio. So effective is still ES over ER. Oh, sorry, which is also equal to IR over I. Yeah, so it's still the same. Here we have IS. I forgot to write this one down. Okay, so that's what we have so far. Right. So what do we want to do here? Now I'm just gonna be writing some equations and stuff, but this stuff you already, some of the things you already know from what is that? Transformers. Just that we are just giving them in different terms now. All right. So let's look at this. If we look at the Transformer EMF equation, let's start with that one. For those that remember, the Transformer EMF equation was E is equal to what? 4.44 times N times the frequency and multiplied by, I think there was a phi somewhere here. 4.444 N5 frequency. There was a phi somewhere there. If you still remember this, what else did I leave out here? It's still fine. I think this is the formula. It's just maybe the arrangement, but that is the formula. This is the Transformer EMF equation. All right. So now with this one, that means that if I'm talking about the stator voltage, it would be 4.44 NF, now N stator. Now you should know that the frequency here, remember this frequency is the one that is coming from the source, usually 50 Hertz. So that's what we call S. That's the frequency of the magnetic field. Yeah, it's the frequency of the magnetic field. I think this one is supposed to be maximum, I think, if I'm not mistaken. The frequency of the magnetic field. All right, but now if I want ER is to be 4.44 NR. Now F must also be FR times the flux. Okay, the flux is the same. Okay, so it's just the frequency that changes and the number of turns. But now let's go back to this frequency. We defined this frequency before. This is the rotor frequency. Yeah. So the rotor frequency, we defined it as FR is equal to S times F. Yeah. Therefore, the rotor EMF can be written as 4.44 NR SF times the flux. So I can actually factor out the S, then I'll have 4.44 NR F the flux. Now this guy that we have here is the same as this one. Okay? Same as that one. It's the same as this guy. Yeah? Okay, but all right, so it's fine. I want to call this guy E naught in this case. E naught. You just know why just now. So if I say, then I'm going to have E naught. This is E R. All right. So what I'm saying now here is that the EMF that is induced here is equal to 4.44 times NR times S times F times flux. But if I factor out the F, I have this EMF here. Now, let me show you something. When S is equal to 1, those that are studying know what it means. When S is equal to 1, that means we're at standstill. They give it a lot of different names, blockage, whatever things, a lot of things, blockage. You check in your notes, it stands still. That means this is when NR is equal to 0. And for those that remember, S is equal to NS minus NR over NS. So when NR is 0, then you just have a 1 here. So that's when S is equal to 1. So it stands still. That means the instant we are switching this on, the instant it's connected to power, it's not yet moving. So that means there is no relative motion between the rotor and the magnetic field, the stator magnetic field. So S is equal to 1. So at that instance, we will have the EMF induced there. We are going to call it E naught. So E naught is the standstill EMF in the rotor. So it's what? Is the standstill EMF in the rotor. Okay. Let me put this one not here. It's fine. And then this one will be rotor, so that it's consistent. All right. We are just talking about the secondary side only. Let's ignore the primary side. Okay. So this we call it the standstill EMF. The EMF when S is equal to 1, when the rotor is not rotating. Okay. Are we together? When the rotor is not rotating. All right. Good. So that's E naught. Then now you will see now when the rotor begins to rotate, as we have now, we will have this in existence. Okay. So this S changes. So we can say when S is equal to 0, we look at it, S is equal to 0. This one you can now see, in this case, you can now see that ER will be equal to E naught. So the rotor EMF at standstill will be equal to that one, right? But when S is equal to 0, S is equal to 0 when NR is equal to NS. That means the rotor is rotating at the same speed as the magnetic field, okay? So if you substitute in this case, you see that your S is gonna be 0. Therefore, that means when that is happening, since they are rotating at the same speed, there is no flux that is being cut. There's no magnetic flux cutting. Therefore, you're gonna have 0 times E naught. That means there is no EMF in the rotor. Obviously, because if there's no flux cutting, there is not, the Faraday's law of electromagnetic induction does not apply there, because there's no flux cutting. They say that there is no induced EMF in there. All right. So the value of ER ranges from 0 to E naught. So E naught is the maximum. It ranges from 0 to E naught. So that means our ER is actually proportional to the sleep. So if the sleep becomes bigger, our ER becomes bigger. If the sleep is smaller, then the ER is smaller. Okay. That is the first part that I wanted you to see. Okay. We can also look at what? The parameters that are in the rotor also, in the rotor coils. Now, we know that X is equal to 2 pi F L, that's inductance. So since you see that there is a change in frequency, therefore that means the reactance in the rotor must change. It must be changing. So now if I put FR here, then here I'll put LR. Ne? And already I know that FR is equal to what? FR is equal to S times F. Therefore, XR is equal to 2 pi S times F times LR. So if you factor out, you're going to have S there, 2 pi F times LR. All right. Now this part is basically X naught. It's this part here. So X naught, now you already know it stands still. Yeah? So we are going to have X naught. So X naught is the reactance of the rotor at standstill. Since the reactance is affected by frequency, it means the reactance is going to change. Yeah? So the reactance at standstill is X naught. All right, it will be changing. Then does R, the resistance of the rotor coils, change? We all know that the resistance of copper wires or wires is not affected by the frequency. So this one is constant, doesn't change, does not change. All right. Now with these new parameters, I can actually redraw that circuit. I can redraw the circuit. Okay. I'm drawing it in an ugly manner now. All right, so we have the reactance there and the resistor there. So now the only difference is now the rest is the same. This one, you know, this side is not going to change, it's still fine. The difference we have now is that here we're going to have ER now, which is going to be equal to SE naught. And then here we're going to have XR, which is now going to be written as XS naught. And then we have our R remaining the same. And our I are remaining the same. So you can instead of putting ER, you're going to put this. Instead of putting XR, you're going to put this. So we are going to work with this now. Right, because X naught is easy to calculate. X naught is just the frequency, original frequency, and original inductance. So the naught values are easy to calculate because we have all the parameters. But when it comes to calculating ER now, we need to find the sleep and stuff. So if you can represent it in this manner, you know, things will become easier for you. All right. Now let's look at something. If you want to calculate IR, because I'm just looking at all the parameters on the rotor circuit, because that's the one that is different now. If I want to calculate IR there, I know if I want the magnitude, it's gonna be ER over that over the impedance. The impedance, the rotor impedance. And I can see that in this case, my rotor impedance is equal to the square root of, don't forget these things, guys, XR squared plus RR squared. Okay, I can rewrite this as what? Let me just start with the R squared. r squared plus, now xr is xs naught, again square this one squared. So that is our impedance. So that means in this case I can rewrite this as, now since er is equal to s e naught, I can write it like this. And this is our current, our rotor current. Okay, this is our rotor current. Interesting stuff, eh? Okay, so we have the rotor current. If you want to calculate it, you can calculate it in that manner, which is fine. So what else do we want to look at here? Now, let's look at it this way. Let's look at it this way. If I want to, let me just go back to the slide. Should I go back to the slide? Let me go back to the slide and see, so that it guide me to what I'm going to look at now. Okay, it wants me to calculate the angle with the phase angle, which you guys know. So it's obviously it's the arctan of xr over rr. And if you want the power factor, let me just write it down so that you see, but I know you guys already know it. So if you want your arctan, your angle, it's just gonna be most xr over r, which is the same as xs naught over rr. And if you want your power factor is gonna be cos of theta r. You know this stuff. This is not stuff that I have to worry about. We already know this. So let me see the next thing that I have to talk about. Yes. Okay, so let's do it this. Now I can also write the current in terms of its phasor. Is a phasor quantity. Ne? So the current is a phasor quantity, IR. It should be equal to, ER is a phasor quantity also, ne? Over, now we have ZR is a phasor quantity. That means here we are going to have an S, E, I'm using a slippery support, so then here we're going to have R plus J S X naught, right? Then from here, there's something that they want to do. We can divide throughout the upper part and the bottom part. We want to just make a slight difference. If we divide the top part by S, both the numerator and the denominator by S, we are going to get E naught at the top, and the bottom we're going to get ER over S plus J X naught. All right. Now we now have a new guy that we have to define here. So we now have this guy here. Right. So now that means when you have such a thing, it means now if you want to find if I'm going to draw the circuit, I'm just going to draw the rotor circuit here. Okay? I'm not drawing the stator circuit, I'm just going to draw the rotor circuit. So it is coils, right? So here, if I look at this, because this is now IR, okay? So if I look at this, what I'm going to do is I will have E naught here. So I'm going to represent it using standstill quantities. Then on this coil here, the reactance, I'm going to have JX naught. But then when I'm here now, I'm going to get something here, a different value of the resistance. Now the resistance I'm going to use is called, it's that one now. Normally they put something like that, yeah? Here. All right, so now This is called effective resistance. No, it's called an hypothetical resistance. Yeah? It's an hypothetical resistance. Right. Yeah, also can also be called effective resistance. So it's the same. Hypothetical resistance or effective resistance. Yeah, hypothetical because it doesn't really exist. It's just us manipulating, the equations and what you know. That's basically it, but it doesn't exist like that. Right. So now, if we have such a hypothetical resistance, we can now begin to compare certain things now. Since our IR is that one, we can now say in the case where, case one, when S is very, very small, approaches zero. Ne? When S approaches zero, when this value here becomes very, very small, what happens to this whole value? In that case, R over S becomes very, very large. If we're comparing the reactances here in the impedance, you see that this becomes very, very big compared to this one. So it becomes much larger than X naught, okay? And when X is approaching zero, and when X approaches zero, what happens, what is the condition for S to approach zero? S approaches zero when the relative motion between the magnetic flux and the rotor is becoming smaller. Remember, S is equal to NS minus NR. So when that NS minus NR is becoming smaller, it means our S is becoming smaller, all right? That means our rotor is now moving faster, okay? Our rotor is moving faster. So when that happens, the effective resistance becomes way larger than what? Than the standstill reactance, okay? That means then our current is only gonna be affected by this guy. So current is gonna be E naught over SR, so like this, yeah, R over S, because this one we just cancel it to be zero. So when this part is larger than this one, we consider it to be zero. So our current is going to be that. So now if you look at that, this guy is constant and this guy is, this guy is constant, ER, and RR is also constant. This value here, RR is constant. So since these are constants, you can actually see that eventually here you will have S E naught over R, and then I can actually say that that is proportional to S. So IR will now be affected by S, directly proportional to S. It makes sense. Let me just take time to explain why it makes sense. Right. Remember, this is a constant. That's why I can put the directly proportional to thing here. Why does it make sense? The rotor is now moving faster, right? The rotor is now moving very fast. And as the rotor is moving faster, it means the load is now. That means that, no, let's not talk about the load. That means that this value is going to be bigger, right? When this value is big, it means the resistance in the rotor circuit is now very large. When the resistance in the rotor circuit is very large, what is going to happen to the current? The current is going to be very, very small, right? So that makes sense to say IR is directly proportional to S, because as S becomes very small, this resistance becomes big and the current also becomes smaller. That's why they are directly proportional to each other. Okay. And the case 2 is when S what? Becomes very large. It becomes very large. Cross approaches 1. Remember, the maximum value of S is 1. When S becomes very, very large, what is going to happen to this quantity? This quantity is going to become very, very small. So it will become smaller. S becomes larger, this quantity becomes smaller. And then that means that X naught is much greater than that RR over S. then it means that our current is now going to be given by E naught over, it's going to be given by E naught over XS. But these two are constant terms. That means our current will now try to be what? Constant. Our current will be reaching a constant value. Constant value. Our current reaches a constant value. All right. So remember, S approaches 1 when the speed in the rotor is 0. So when the rotor speed is 0, then that is it. When the speed in the rotor is now 0, so our current is trying to go to 0. Actually, its current also tries to go to 0, and then it becomes a constant value. Okay? All right, so it's fine because we know that when the rotor is 0, what happens? When the rotor is 0, we have a maximum EMF. Yes? Yeah, we have the maximum EMF, sorry. And then we have the maximum current, which is a constant value, not 0, but it will be a constant value. All right. Okay, so that is it with this so far. Okay, that's it with this that we have so far. Now with this, you can also see that what you can do is you can refer quantities. You can refer these quantities onto the stator circuit. If you refer those quantities onto the stator circuit, what you have is this. You're gonna have this. Yeah, almost about to finish because I think I've Okay, right. So this is an equivalent circuit. All right, so this is IR. Just want to I want to work on this only so far. And this is J, X, S naught. And this is what? RR over S. And this we already know, it's XM. I want to concern myself on these guys here. All right, so now the current is actually flowing, the current flowing in the, because we have referred these terms. This is a referred quantity, that's a referred quantity. The current is flowing in this circuit now. So I can actually say that the power that is supplied to the rotor, the power supplied to the rotor. What is the power supplied to the rotor? It's easy. We have this is our rotor equivalent effective resistance, and this is the rotor current. So the power supplied to the rotor is actually equal to IR squared times IR prime over S. Simple, né? But this is the power supplied to the rotor. But what about the power lost in the copper wires? Remember the actual resistance. This is effective resistance, but the actual resistance, we all know the actual resistance of the rotor coils is equal to RR, and it's constant, doesn't change. So this is what gives us the losses. So the power losses in the rotor are IR squared times IR prime. So what happens, the power that is supplied to the rotor is that one, the power that is lost is this one. So where does the rest of the power go? So let's calculate that power, the rest of the power. Then I'll define what it is. So the rest of the power is going to be the power that is supplied to the rotor minus the power that is lost. Sorry. Okay, now here you can factor out I, R, then you get R over S minus R. So this one becomes It becomes I. If I make S a bit of formula, I'm going to have IR prime minus S times IR prime. I can also factor that the IRR. So we're going to have IR prime squared multiplied by 1 minus S over S times So now, okay, sorry. So now, what is this power? Where is this power going? We supplied this power. We lost this power. So what is this power that remains? Definitely it's not zero. We can't supply power to lose all of it. So this power that we have here is the mechanical power. It is the one that now turns the shaft. It is the one that is now responsible, that is now on the shaft actually. Right, so some of the power is lost in the copper wires. So the rest of the power, because our goal was to turn a shaft, so the rest of the power goes to turning a shaft. All right, so this is the equivalent now. Now, if we were carrying, maybe if we're lifting something, it's rotating and it's lifting some weight. Now, this is the load. So this is the electrical equivalent of our load. The electrical equivalent. If we are going to express our load in terms of electrical quantities, it will be these guys that will represent it. That means now we can again modify our circuit. This circuit can now be modified again. So on the second part, so the first part is the same. The first part is the same. The second part is now what I'm going to modify. So remember, this guy came from saying the power delivered. Hey, I'm using this now term. It's called the power delivered to the rotor, is equal to the power that was lost. So I'm going to say rotor copper loss, CU, PRCU, rotor copper loss. All right, plus obviously it should be mechanical power. Mechanical power. So therefore, mechanical power, Pmech, must be equal to the power delivered minus the power rotor copper loss, the one that was lost in the copper wires. That means I must have two quantities. I must have two quantities now, here and here, that are using my power. So I have this one, which is the rotor resistance, obviously, that's the rotor copper loss, and I have this one, which is my load. So now I'm going to represent those here. So I know that we have this guy, right? But I also know that now I have my rotor copper loss. I brought it again. But now, here now, we are now going to connect our load the normal way you would know in transformers now. But our load is 1 minus S over S, because that represents what was really lost. What really went to that's mechanical power. So what was lost is here, and then here we have the reactive, whatever things. And then here we have IR, right? So this guy is representing our load. So now that is the circuit that we have, a nice circuit. That's the one that we will work with throughout in our calculations. So the first things, we are not going to use those. Unless he says use this part, we are mostly going to use this circuit because we are concerned about what goes out, okay? Now, the other thing that you must remember, so I'm going to close this. I don't have time to do an example now. Maybe we can schedule just a class for just that calculation of for an example. right? But you analyze this circuit the same way you're analyzing transformers. Now, I just want you to know that this is just extra information. I don't think I'm supposed to be giving this now. That we have power input, P in, from our sources. And that when that P in goes, it is lost here as copper losses in the stator copper losses. And it is also lost in the form of core losses. And then from there it is there's some power lost in the air gap. Air gap power loss. I think, is it air gap power loss? Okay, I'm trying to remember this from last year anyway. Okay, there's a power that crosses. Okay, it's fine. It's called air gap power. The power that crosses the air gap. Remember, we have copper losses here, and then we have these losses here. And the one that goes onto the secondary circuit is what we call air gap power. Yeah? All right. Then from the air gap power, we have copper P rotor copper losses also. All right? P rotor copper losses. And mostly we're supposed to have mechanical power. But then what happens is that there are going to be other losses like friction and windage losses. Because this thing, when it's rotating, there will be friction with the air, and the friction within the mechanism, and then also with air. Yeah? Then eventually what we have now P out. So I think this one here should be called P developed. We'll look at this later. It's just, I just wanted to talk about it, but we'll look at it later. So it will be something like that. It's interesting. This machine is interesting. Let me just say the P developed is here. All right. So we will be having losses. So you can see that, you actually see that in some cases, because power loss, power loss is the same whether it's on the primary or the secondary. Eh? It's the same amount. So in some cases they remove this part. Then they combine the core loss to the rotor losses. So they will just subtract that loss from here all at once. When they are subtracting the windage losses, actually not here, they subtract it here. Core losses. Eh? So usually they will put it here, then they remove it from here. So that means this circuit will not have this part here. You just have this part here. You check that in the notes. It's well explained in the notes. Yeah. So basically, these are the equations that we'll be using. So what I'll do is, I think I will have to make another video calculating, right? So that when you're going to do your quiz, you will not have much problem. So I'll make another video just focusing on calculations, probably tomorrow. Okay. Have a good day.